Okay, welcome to week 1 of Year 12 Physics. This will be the first of, I hope, regular videos. What we're going to go through first is a bit of revision of Year 11, but it's really important stuff that we rely on in Year 12, so it's worth spending a bit of time going over. So first thing we're going to look at in this video is vectors and scalars, the difference between the two and some common ones, and we're going to look at motion graphs, so position time, velocity time, acceleration time graphs, and the information that we can get from those. Other topics we'll be doing this week are equations of motion, Newton's 3 laws, and inclined planes, all of which you've probably seen before, but you've probably forgotten a lot of. So, firstly, vectors and scalars. You'll recall that vectors are defined by magnitude and direction, whereas scalars are magnitude only. Vectors we often represent as arrows with numbers above them, whereas scalars will usually only be a number with units as well, units for a vector as well. So it's important that when you're giving an answer as a vector, you give both magnitude and direction, whether that's as an arrow, whether that's as a compass bearing, or even if it's a one-dimensional question, from motion back and forwards along a straight line, it can just be a positive and negative, depending on the context of the question. But important that vectors are always in terms of a magnitude and a direction. So examples of vectors are things like velocity and acceleration is another one. Scalars, on the other hand, things like speed or time, mass, things that don't have a direction. So when we multiply two scalars together, that's straightforward. You just get another scalar. A vector times a vector, of course, gives a vector. The actual direction of those vectors isn't really important. We don't do vector multiplication in physics, in Year 12 physics. When we get a vector times a scalar, it's important to remember that the answer will always be a vector, and it will be a vector in the same direction as this vector. So they will have the same direction. So if you have a vector in that direction, in your multiplication, your answer will be a vector in that direction. Things like F equals m times a, Newton's second law. Force is a vector, acceleration is a vector, they will always be in the same direction. So that's where that's important. Okay, adding vectors together. Vectors in one dimension are straightforward, positives and negatives. We assign one direction as positive and the other direction as negative. But when we have two dimensions, it gets a little trickier. So here's a classic question where we have a boat traveling across the river. Let's say he's moving across at 4 meters per second, and there's a motor or maybe some oars pushing him across the river at 4 meters per second. So he's going 4 meters per second north, and the river itself is flowing at 3 meters per second to the west. So what will be the total velocity? What will be the velocity of the boat itself? So all we need to do is add together our two vectors. So we're always adding them head to tail. Always the head of the first to the tail of the second. Doesn't matter which way around you do them, but always head to tail. And in our course here in Year 12, it'll always be at right angles. So we have 4 meters per second there, and we have 3 meters per second there. So we get a nice right angle triangle. So here's the total V, there's 3. Right angle triangle, and so we know by Pythagoras that V squared equals 3 squared plus 4 squared. V is the square root of 9 plus 16, which is 5. You may have recognised that as a Pythagorean triple of 3, 4, 5. So the total velocity is 5 meters per second. Not 4 plus 3 equals 7, as some people might have thought. Because those vectors are added at right angles, it makes a right angle triangle. You have to use Pythagoras to find that overall. We'll find Pythagoras popping up a lot in Year 12 physics. I'm sure you've noticed it already. Okay, vector components. This is where we take one vector and break it up into two smaller vectors or components at right angles. So the net force or the net vector is normally the hypotenuse of a right angle triangle, and we're normally breaking it up into two. So here is a common example. It's an object being dragged across a floor. It's in motion in this direction across a floor here. And there's 100 newtons, let's say 100 newtons of tension in that rope being pulling along there. What is the force that's actually sliding along? What force is actually along this bit here, dragging it along the floor? What's the horizontal component of that force? It's at 35 degrees to the horizontal. So the horizontal component of that force will tell us something about the frictional force between the box and the floor. So we make up our right angle triangle, and we see we have the adjacent side here and the hypotenuse along here. So by our knowledge of trigonometry, we know this is the cos ratio. So we can write the cos of 35 degrees equals the adjacent, we'll call it A, over the hypotenuse, 100. And so A is 100 cos 35. And so A is 81.9 newtons, a large part of that 100 newtons, but not quite. So there is 100 newtons being applied at 35 degrees, there is 81.9 newtons dragging it across the floor. So we've broken up that net force there into two component vectors, there and there. Okay, displacement and distance. So one of these is a vector, one of these is a scalar. Displacement is our vector quantity, and distance is a scalar. So displacement, we often give the symbol x. Some people might use s. I tend to use x. Distance, we often call d. So here is Sally in the red and Tom in the blue, and they're having a race around the block. Tom's on crutches, I think, so he goes this way. Sally runs all the way around here. So you can see that Sally has covered a greater distance than Tom. She's run 20 plus 15 plus 20 again. She's run 55 metres. So the distance that Sally's covered is 55 metres. Tom on his crutches has only gone 15 metres. Displacement, however, you'll recall is the difference between the starting position and the ending position. So because they both started from the same point and ended at the same point, their displacement will be the identical 15 metres, the difference between where they started and where they finished. So they have identical displacement even though they travel different distances. So remember, displacement is the vector quantity, so I need to specify a direction here. We'll use a compass direction. We'll call it 15 metres east. Remembering that is a vector. Okay, another scalar vector pair is velocity and speed. Velocity is the vector quantity, usually given the symbol v, also can be u for initial velocity, and speed I like to call s. So velocity is defined as the change in displacement over change in time. Speed is simply distance over time. So again, Sally and Tom. Sally having run all the way along here, her speed will be her distance over time. So you'll recall her distance was her distance was 55. Sally's distance was 55, and let's say they did this in 10 seconds. They both reached the end at 10 seconds. So her speed was 5.5 meters per second. Tom's speed was, well, his distance was 15 meters in 10 seconds. So his speed was only 1.5 meters per second. Their velocities, however, Sally's velocity will be her displacement over time. So her displacement, you'll recall, was 15 over 10, 1.5 meters per second east. So too was Tom's. He had the same displacement, so his velocity will be identical. 1.5 meters per second to the east. Acceleration. Acceleration is a vector, and it is the rate of change of velocity. So how quickly your velocity is changing. If you speed up or slow down very quickly, you have a large acceleration. If you do it slowly, you'll have a small acceleration. So acceleration is defined as change in velocity over change in time. Now, velocity, we define final velocity as v, initial velocity as u. So acceleration can also be written as v minus u on delta t, the change in time. So here's an example: an athlete doing a shuttle run moves at 15 meters per second east. So here he is going 15 meters per second to the east. And then he stops, turns, and moves 15 meters per second back to the west. Here he is going the same speed back to the west. And this all takes 3 seconds. So his change in time will be 3 seconds. So what is his average acceleration? So what is the acceleration over this whole 3 seconds? So acceleration will be final velocity minus initial velocity over time. So his final velocity was 15, his initial velocity was 15, but they're in opposite directions, and since they're vectors, we have to define one of these as positive and one of them as negative because they're in opposite directions. So let's define this direction as positive. It's customary to define left to right as positive, but really you can do it anyway. So we're going to define this direction as positive, so this velocity will be positive, this velocity will be negative. So his acceleration will be final velocity, negative 15, minus his initial velocity, minus positive 15 over 3. So his acceleration will be negative 30 on 3 will be negative 10 meters per second squared. Meters per second squared because for acceleration we have meters per second on the top line, that's velocity, divided by seconds. So we have meters per second, meters per second squared for his acceleration, average acceleration over that time.